Okay, so as Nohan has joined, so I'm going to uh, record this class. Usually, I also record. So today, I also record the class and I'll upload it in on YouTube and I'll share the YouTube link in the spreadsheet. And from the recorded lecture, you can go through. Uh, you can go through the video, and if you have any doubt, then you can ask me in next class, or you can also uh, con- send me the questions as well. Okay, so let me start with sharing my screen. Okay, it's not. Let me check. No. Okay, okay. So now it's connected. Okay. So today we'll discuss few questions and problems. As now we are mm, very close to the end of the course. So now for today's class and rest of the classes, we will discuss the various questions from different portion of this course. So today we'll also discuss few questions from thermochemistry and then we'll discuss other questions as well. Okay. So first I'll write down the questions and then we'll solve it. Okay. So question number one is the molar heats of combustion. Okay, let me write it. Yes. The molar heat of combustion of C2H6, which is a gas, carbon in graphite form, and H2, that is also in gas form. The molar heats of combustion are given for this species. Okay, uh, are 31.62 kilocalorie, 94.05 kilocalorie, and 68.32 kilocalorie respectively. Okay. Now they ask that the standard heat of formation, okay, of C2H2 gas. Okay, so these type of problems from thermochemistry did not discuss in the class. That's why I thought to discuss basically. because these questions are also important. I will discuss few questions, 3 to 4 questions, so that a basic idea can be developed. Okay, so now to solve this type of question, we must know about the what is the definition of heat of formation or heat of combustion, like these things, molar heat of combustion. This definition we first should know. Then we can easily do this type of question. That is not a very difficult. Okay, so what is the heat of combustion? This is given heat of combustion, and it is molar heat of combustion actually. Okay, so what is the definition? Let me first discuss that. First is heat of combustion. What is the heat of combustion? Let's say for a combustion process, you are taking a species. Let's say you are taking X, any X species that is in gaseous form, and when it comes close with oxygen, combustion occurs, and after combustion, it will it will produce oxide. We don't know the valency of O2, but with valency of X, but it will be some oxide, XO2, like these things. We don't know. It may be X something depending upon the. Just we have to understand the things first. Let me write it. The oxide will be produced. That is also gas. Okay. So now, if you take 1 mole of this species of X, gaseous species X, and after the combustion, net change of enthalpy. That means the enthalpy of product minus the enthalpy of the reactants. If you do that, if you calculate that, the net change in the enthalpy, that is called the heat of combustion. Means that del H equals to H of product minus H of reactants, or H of, let capital P, capital R. This del H eventually is the heat of combustion. Okay, if you take if you take taking the sample, the species X, 1 mole, if you take the 1 mole of species X, then this del H is called, would be called the molar heat of combustion. Okay, so similarly this is a heat of combustion. So what would be the definition for heat of formation? Okay, heat of formation, it is also quite similar. The enthalpy change to produce some species. Let's say you are producing species X from, you don't know, from some substance A to B, you are producing species X. So to produce 1 mole of X, species X, that net change of enthalpy is called, now again the del X, to produce 1 mole, if that is 1 mole only, then that is called the, that will be called the heat of formation. Okay, so that's the basic definition. Now, if you solve this question, then it will be easy to understand. What is given in the question, that heat of combustion for C2H6, C and H2, these are given. That means first you have to write down the combustion process for these three substances. First is the C2H2. C2H2. So C2H2, which is a gas, when it comes in contact with oxygen, then what it will produce? We have to must know it. It will produce oxide. There is mm, there are two species are there basically in C2H2. One is our carbon dioxide, carbon, and another one is hydrogen. So eventually the oxide will be carbon dioxide and water, H2O. These two oxides will be produced basically. Now you have to balance the equation. So if you balance it, then eventually it will be, so 2 will be multiplied there, then it will be 5 by 2. Okay, so this is the overall process. This is the combustion process. You have to first balance equation. After balancing equation, you can calculate the del H. Okay, and the del H for this process is given, that is minus 31062 kilocalorie. Okay, so this is heat of combustion. That means the heat uh, generating during the combustion process. That means that heat is this heat, this amount of heat is coming out. Okay, so that's why the minus sign will be there. It is not absorbed by the system. Okay, this amount of heat is coming out from the system to the surrounding due to the process of combustion. So that's why there should be a minus sign. Whenever we are talking about the heat of combustion, you must include the minus sign, because the combustion means that the heat is generating. So you have to taking care, you have to account that minus sign. Okay. So now for other two processes, second one is for carbon and other one okay. For carbon it is easy. No, for carbon it is graphite. When you burn carbon, burn carbon in air, it produces carbon dioxide, CO2. So it is balanced, already balanced, and del H is also given for this combustion process, which is minus 94.05 kilocalorie. And the third one for H2, we know this, water will be produced, and for this process the del H is minus 68.32 kilocalorie. Okay, so now w- these are given. Now what we have to find out? We have to find out the heat of formation for C2H2. So sorry, for that we have to write down the formation equation, the formation reaction of C2H2. So C2H2, it will be formulated from its ingredients, which is carbon and hydrogen. So it should be from carbon and hydrogen. Now you balance it, so it will be 2C plus H2. We have to calculate the del H for this process, right? So that will be our heat of formation for C2H2. And we have to keep this 1 mole, obviously. Then only it will be valid. So you can see here for each cases, this species is considered as 1 mole. So that is by definition. So now we have to formulate this equation. The procedure is like this. We have to formulate this equation by from these three equation, known equation, and we have to calculate the del H. So we can do like this. We need C2H2 in this way. So let us give the name of these equations first. Let's say this is our equation A, this is our equation B, this is our equation C. Yes. So what we can do, 2 into B plus C minus A. If you do this, then what we will get, 2 into B means 2C plus 2O2, and in this side it is 2CO2, right? Okay. What is C? We need more space. Okay. C is H2 plus O2. Let me write it, H2 plus O2. So here it will be H2O. And minus A. A is C2H2 minus 5 by 2 O2. And here minus 2 CO2 minus H2. So you can write it as 2C plus H2. O2 will also be cancelled out to C2H2. Okay. So this equation we are getting. So just to find out the del H of uh, del H for formation, del HF. So what will be del HF? Del HF will be 2 into del HB plus del HC minus del HA. So just calculate it. So it will be 2 times minus 94.05 plus 68.32 minus 68.32 minus of minus 310.360 kilocalorie. So just let me thumb this. It will be 2 into 94.05 plus 68.32 minus 310.6. Okay, so it is 54.20. This will be our heat of formation for C2H2. Okay, so this is the procedure basically. So you have to follow this procedure to solve this type of question. Okay, so now going into question number 2. Hmm. The heats of combustion again of ammonia H3 and H2 are 9.06 and 68.9 kilocalorie respectively. Okay, so heat of combustion for NH3 and H2 are given here. The heat of formation of ammonia is, so it's similar type of question. Okay, it's better to do for practice. So for ammonia, right, we have to first write down the equation for heat of combustion. So ammonia plus O2, what will be? It will be NO2. No, in case of ammonia, it is not NO2. Just you have to know this equation, otherwise you can't do. It will form N2 plus H2O. Okay, now you can balance this. Here will be 2, then it will be 3, then it will be 3 by 2. Okay, and this is given, this del H is given. Let's say this is our reaction A. So del H A is 9.06 kilocalorie. Okay, now for B, what is the reaction? H2. H2 we know, it's very easy. H2 plus O2, it will produce our H2O. And del H for this process is given as minus 68.9 kilocalorie. Okay, minus sign we have to always taking care. You have to take care. Okay, minus sign will be there. So now these are given, and we have to find out the formation, heat of formation for the reaction for the ammonia. So for ammonia, we have to formulate ammonia from nitrogen and hydrogen. Just we have to balance this equation. It will be 2, so it will be 3. Haber process. But we have to keep in mind that for each case we have to consider 1 mole of species. Only 1 mole of this species. So because these are the molar heats, molar heat of combustion. Okay. Now to make 1 mole, it should be 1. So we have to divide it by 2. So it will be 3 by 4. It will be half. It will be 3 by 2. This is 1 exactly correct. Here it will be again 1. So again it will be half. It will be 3 by 2. This is the Haber process, we know. So we have to find out this. How you can formulate this equation from A and B. Just okay, H2 is there. Multiply it with 3 by 2. If you multiply it with 3 by 2. Okay. Just 3 by 2 into B minus A. What we will have? We'll have 3 by 2 H2 plus 3 by 4 O2, and this side 3 by 2 H2O minus of A. A is NH3 minus 3 by 4 O2. Excellent. And here it will be minus half N2 minus 3 by 2 H2. Good. So eventually it gives us the equation, this equation, right? It will be 3 by 2 H2 plus half of N2 to NH3. Okay. So eventually the del H formation of ammonia will be 3 by 2 into del H B minus del H A. Now just we have to put the values. 3 by 2 into what is the HB? HB is minus 68.9 kilocalorie, and this will be minus minus plus 9.06 kilocalorie. So it will be minus 68.9 into 3 divided by 2 plus 9.06. So eventually it is 94.29 kilocalorie. The heat of formation should be always positive because this amount of heat we have to give from outside. Then only the uh, our expected product will be formed. Okay, so this is the solution. Now going to question number 3. Okay, this is kind of different question. 1 mole of naphthalene was burnt in oxygen. Oxygen gas at constant volume to give carbon dioxide gas. Okay, and liquid water. at 25 degrees centigrade. Heat involved, heat evolved was found to be 5138.8 kilojoule. The enthalpy of reaction at constant pressure. Okay, the enthalpy of reaction at constant pressure will be. So we have to find out the enthalpy of the reaction, means the enthalpy change. Okay. So what is 1 mole of naphthalene was burned? What is the uh, formula of naphthalene? This is our naphthalene. This is naphthalene. That means for 1, 2, 3, 4, 5, 6, C10, H12, not H12. 1, 2, 3, 4, 5, 6, 7, 8. C10H8. Okay, which is a solid species. It is burnt in oxygen, which is gas, and eventually it will produce CO2 plus H2O. Now we have to balance this. 10 will be there, 4 will be there, so oxygen is 24. Okay, so this is a balanced equation. Now we have to find out the that okay, the given is that the heat, how much heat possible, that is given. Okay, just we have to find out the uh, change of enthalpy. Okay, how we can approach this? For this reaction, there is some del H, there is some del U, right? And we know del H equals to del U plus P del V. This del H is enthalpy change, del U is the heat, how amount of heat. Okay, because you can think like this. Hmm. Heat is given, right? So you can du equals to vdp minus sdt. No, that is dg. So du equals to, from first law of thermodynamics, we know that d cross q plus d cross w, like this. Oh, you can consider the negative sign as well. That is not important, but there is no mechanical work. So d cross w is eventually 0. Okay, so that's why that this d cross w eventually is the mechanical work. But this du is actually heat molecule. Okay, yes, that's correct. So now if you put it for gaseous species, these are the gas for gaseous species. One minute, just put this electronic charge. That is going. Okay, sorry. So del A is equal to del U plus P del V. So now, yes. So that del U is given here, that is heat evolved, and P del V. What will be P del V? P del V will be, uh, we know PV equals to nRT for gaseous species. Here P del V should be equals to del N GR. Okay, for gaseous species, now change in del N G is the del N G will be the uh, N product minus N reactant. Number of moles. Product minus number reactant. So you can directly write it that this is actually our QP equals to QV. We know that QV D cross Q equals to, we know, DU plus D cross W, or this is actually minus PdV. So we know that D cross V is eventually the DU. So, or you can write QV is del U. So that we have written. And for enthalpy, that is equals to QP, heat exchanged in a constant pressure. So this QV is given uh, for constant volume case, that is given. So now you can write it as QV, it is del NgRT. So just now you have to calculate. So QP will be, what is QV? 5138.8. Now del NgRT, del Ng we have to find out. Del Ng will be Np minus Nr, as I discussed. What is Np? For gaseous species, this is gaseous, this is liquid. So 10, Nr is 12. So eventually it is minus 2. R is 8.314. In joule, we have to consider, right? But this is in kilojoule. This is in kilojoule, okay. 8.314. What is T temperature here? 25. Okay. Means 298. This is in joule. So we have to multiply it with 10 to the power minus 3. Then it will be in kilojoule. So just we have to consider this. So it is, okay, okay. My mistake, the minus sign. Right. Now it's because this heat is this amount of heat while combustion, uh, because it is burned, right? So this amount of heat is going out, as we discussed in previous question. So it will be 8 kilojoule. Okay, so this is the question. Okay, so let's see. This unstable. Okay, now we do the question number 4. Okay, the enthalpy of combustion of glucose. Okay, which is C6 H12 O6 in solid state is minus 2816 kilojoule per mole at 25 degree centigrade. Now calculate del HF 0 of C6 H12 O6 values for CO2, O2 gas, H2O liquid are minus 393.5 and 285.9 kilojoule per mole respectively. Okay, values are given for CO2 H2O. Okay, okay. So first we have to understand the reaction. What is the reaction here? Mm, the glucose is burning in presence of the oxygen. This is H12O6. In presence of oxygen, it will burn and produce, CO2 and H2O. Now we have to balance the equation. 6 will be there, 6 will be there as well. So now the oxygen will be 18, means there will be 6, 12, 6 is there, so 6 oxygen will be there. So this will be the balanced equation. So now the heat of combustion for this reaction has been given. That means we know del HF, we know del H for this reaction, del H which is minus 2816 kilojoule per mole. Okay, now the heat of formation are given. Okay, this is the values of the heat of formation values. For this is not important. This is just representing the components of the CCS. So, okay, del each values for this are given. But now we have to just understand this is actually the questions will be like this. Okay, so there was a typo, I think, in question. Okay, Okay, now this is given. So what we can write now, what is given that the heat of formation of CO2 is given, and CO2 will form from carbon plus oxygen. It is balanced already, and also H2. Oxygen is already gas. So oxygen, there will be no heat of formation for oxygen. Oxygen is a O2, is a pure substance, right? There will be no heat of formation. In case of high water to H2, we have to balance it. We have to keep in mind there should be one. So this is del H formation for CO2, which is already given as, what is the value? Minus 393.5 kilojoule per mole. And for this case, then each F for H2O will be, it is given as 285.8 kilojoule per mole. Okay, so now what we can write? So del H, so let's say we can write this is A, this is B. So 6A plus 6B. 6A plus 6B. What we will get? Then they asked, these are given, okay. H are given, and their H for H value for these are given, and we have to calculate. Okay, right. We have to calculate del HF for glucose, where del HF for del H values for CO2 and H2 are these. Okay, so we have to find out, these are given. That's why I was finding the question. What is the question? Okay, now we have to find out this one. C6H12O6. We have, this will be formed from carbon, hydrogen, and oxygen eventually. So it will be 6, 6, 3. Correct. So now we have to construct this equation from these two equations, these three equations. These three values are known to us, so we have to find out this this del H F for C6H12O6. This value we have to find out. Okay. So let me rename this equation as, this is, let's say, A, B, C. So now 6A plus 6B, let us check, minus C, what we obtain. So what will we obtained? It is C 6C plus 6O2 plus, again this is also multiplied, 6H2 plus 6 by 2 is 3, so it will be 9O2, and this side 6CO2 6H2 minus C6H12O6 minus 6O2. And in this side it will be minus 6CO2 6H2. Okay, so eventually it means that 6C plus 6H2 plus CO2 C6 H12 O6. Hence del H A for C6 H12 O6, that will be del H A of nature of CO2 H2 6 into plus 6 into del H F of H2 minus del H. This is the del H we have already written. So just we have to calculate now. This is 6 into, let me add, it is minus 393.5 minus 285.9, and this will be plus 2816 in all total in kilojoule per mole. Now just we have to calculate this. Minus, okay, 393.5 plus 285.9 into 6, 2816. So it is eventually minus 1260.4 kilojoule per mole. This is a there was a type of people giving the question. Yes. Now going to question number 5. Okay, what they have asked, what is the heat of formation? Let me write. What is the heat of formation of benzene from the following data? Assuming no resonance, okay, bond energies are there. What is given? C single one C bond energy of C single one C is 83 kilocalorie, and C double one C is 140 kilocalorie. And also given that heat of atomization, okay, heat of atomization of carbon, that is 170.9 kcal, and also heat of atomization of hydrogen 52.1 kilogram. So this is also given. So here there is a new term, heat of atomization, right? What does it mean? First we have to understand, then only we can solve this question. So what is the definition of heat of atomization? Bond energy we know, bond energy is also given, but bond energy we know, but heat of atomization we don't know, right? Okay. So heat of atomization means uh, the amount of heat required to form that atom, construct that atom. You can think like that. Here, heat of atomization of carbon is 170.9 kilocalorie. That means you can think that for creating or generating one carbon atom from any other species, we don't know, we need 170.9 kilocalorie. Okay, so that is the heat of atomization. So, uh, while solving the question, you can understand this very clearly. Now we have to find out the heat of formation for benzene, right? So benzene is C6H6, we know, and for heat of to calculate heat of formation, we have to construct from carbon and hydrogen. So this is the okay. So we have to find out del H for this reaction. That will be the heat of formation. That del H will be the del H heat of formation for C6H6. Correct. So now we have to find out this. How we can find out this del H? So eventually del H will be H of product minus H of reactant. You can write like this. Okay. So just we have to calculate H of product and H of reactant, then it will be easy. So first, what will be what will be H of reactants? 6 carbon is there. So 6 into what is the heat of atomization for one carbon? 170.9. So it will be 170.9 plus 6 into what is the heat of atomization for hydrogen? 52.1 kilocalorie, right? So it will be eventually 170.9 plus 52.1 into 6. So it is 1338 kilocalorie. Now what will be heat of enthalpy of product? It will be C6H6. Okay, so C6H6 we know how does benzene look like this. We don't need to consider the the resonance energy. So it is like we all know the structure of benzene. Correct. Here is a hydrogen like this. So just we have to find out here how many C single bond C is there. This is one C single bond C, two, three. So 3 into what is the heat of formation for C single bond C? 83 kilocalorie. So 83 plus. Okay, another one more information was there, sorry. That is CH bond energy is also given. That is also required. Otherwise, we can't solve this question. And that is 99. Okay. So how many C double bond C? 1, 2, 3. 3 into what is the bond energy? 140. Okay. Plus 6 CH bond. 6 CH bond. So 6 into 99. All are minus. Okay. They are minus signs. Oh, here is also. Because these are the like no. Sorry. These are this is the bond. Okay. It's correct. Minus sign will be there. Because these are yes, there will be also minus sign. Minus sign will be there. Okay, but also you have to consider there is 6 carbon plus 6 hydrogen. Uh, Already that you can think like that in benzene also there is 6 hydrogen and 6 carbon. So that uh, energy, that heat of atomization should be also considered, but no, that is not the case. That is already considered in the bond energy, so that we don't have to consider. So what will be the result? It is 83 plus 140 plus 99 into, oh sorry, is 83 plus 140 into 3 plus 99 into 6. So it is 1263 kilocalorie. There is a minus. So what is del H? HP minus HR. So it is plus 1338 kilocalories. So it will be 75. Okay. So that will be our heat of formation, and that is our heat of formation for our benzene. Okay. So going to question number 6 now. Okay. Similar kind of question we will discuss. So, okay. So this is also a similar kind of question. So what is the resonance energy? Here we have neglected the resonance energy, but also there is a resonance energy as well. In this question, we will account that resonance energy. We will calculate for different molecule eventually. What is the resonance energy in CH3 COO8 acetic acid from the following data? Where the heat of formation acetic acid, that is minus 439.7 kilo. And what are the data? Data are bond energies are given for CH bond, CC bond, CO bond, P single bond O, and OH bond. And also heat of atomization given, that is happening. Heat of atomization for carbon, oxygen, and hydrogen. All are in kilojoule. So what are the data? It is 143, it is 348, it is 732, it is 463, and it is 351. And it is 180.0, 249.1, and 716.7. Now we have calculated. So what is the heat of formation? How we can calculate CH3COOH acetic acid? How does it look? You all know. You have to calculate the resonance energy, right? So there is a resonance like this. Okay, so we have to calculate the resonance energy. Before that, how we can calculate the heat of formation? From here, carbon is 1, no, carbon is 2, hydrogen is also, there should be 2, oxygen coming here. Okay, for this reaction, del H is essentially the heat of formation, which is known, which is given minus 439.7. Okay, this is given. This is our heat of formation. And also the bond energies are also given. So first we have to consider we have to calculate the del H by considering the bond energies and the heat of atomization. This experimental result no. But let's say this del H should be equals to del P minus del R. Sorry, HP minus HR. So what is HP or HR? First HR. HR will be this heat of atomization for 2 carbon, which is 2 into minus. All will, there will be a minus sign. So in general, we can keep minus plus again 2 into for H2. There are 4 H2, so it will be 4 into 218 and 2 into 249. Okay, so now we have to calculate this. It will be eventually 716.7 into 2 plus 218 into 4 plus 249.1 into 2. So it is minus 2803.6 eventually in kilojoule. Because all the data was given in kilojoule. This is HR and HP will be CH3COH. Now we have taken calculate the bonds. So here we can see CH bond. How many numbers of CH bond? 1, 2 and 3. So 3 CH bond is there. 3 CH bond is 143. So minus. Again, we are taking that account. Plus. How many number of C single bond C? Just one, right? Just one. So it is 348 plus CO. One CO, one C single bond O and one C double bond O, right? And one OH. So just we have to add each one. 732 plus 463351. And plus X. This X is, let's say, resonance energy because there will be a resonance energy. We have to consider that as well, which we did not consider in the last problem. So it is 143 into 3 plus 348 plus 732 plus 351 plus 463. So it is minus 2323 minus X kilojoule. So now we know. Hence, del H is HP minus HI. And that is also known to us, which is minus 46493. This is 439.7 kilojoule. So, can write HP is minus 2323 minus 8 and HR is 2803.6. It is this. So now we can easily calculate the X. What will be the X? X will be 439.7. Wait, 0, 3.6. 439.7 plus 2, 3.6 to 0. There is mistake. No, it's correct. 920. That should not be positive. Oh, this is negative. Yes. 0.3. This will be the resonance energy. Okay. So I think we have already discussed 6 questions from this thermochemistry part. Let us do some different type of questions as well. Not different type of questions. We have already done this type of question. Just we'll do this type of question again for our practice. Sorry for inconvenience. Okay. So let me find out the question first. Solve. Okay. Just we have to show that to establish the relation between del S, del VT, right? And alpha beta. What is alpha beta? Alpha is our thermal expansion coefficient. And what is beta? Beta is compressibility factor. Thermal compressibility. Okay. So what is alpha? The form of alpha is 1 by V del V del T. And what is form of beta? Minus 1 by V del PT. So we have to establish the relation of del S del VT with these two. So eventually it's clear there is nowhere there is S. So again, so we have to consider our Maxwell square. We know how to use this. Okay. So from Maxwell square, we can directly write what we can write del S del VT equals to del P del T V. So now it's relative, right? But we have to identify del P del T V. How we can, and there will be both same in sign, so sign will be same. So now we have to use a cyclic rule. What is the cyclic rule eventually? Uh, let's say a function which is a function of just like here V, T, and P. Or let's say P, which is a function of V and T. If you think like this, Then you can write del P del V T to del V del T P into del T del P V equals to minus 1. This is the cycle. You can prove this rule as well. There is nothing to difficulty to, there is not, let's try to prove this. If there is any problem, then you can say me in the next class and I will solve. But this is easy to prove. Nothing is there for any cycling rule. Now you can easily find out what we have to find out del P this, del P del Vt. So del P del Vt, it will be equals to minus 1 by del V del Tp del T del Pv. Del V del Tp is known and we can write this as del P del Tv divided by del V del T P. Okay, so what we can write 1 by V into del P del Tv divided by minus of 1 by V del V del Tp. So the numerator is eventually the alpha and denominator is beta. Correct. So del P del P del Vt is equals to alpha by beta. Hence del S del Vt is also equals to alpha by beta. So this is a very straightforward method. So this type of question is very important. While lots of concepts are required, the cyclic rules are important, and also the important concept is the Maxwell square. So now using this relation, we have to solve the main problem. What is the problem? For C6H6, which is liquid, the alpha is given. Alpha is 1 into 10 to the power minus 3 Kelvin inverse, and beta is 9 into 10 to the power minus 4 MPa megapascal inverse at 300 Kelvin and 101.325 kilopascal pressure. Now the change in molar volume, which will be equal to produce an entropy change of 2 joule Kelvin inverse mole inverse at 27 degrees centigrade, assume alpha and beta to be constant. Okay, we have find out the del V. So we know del S del Vt equals to alpha by beta. Alpha and beta are given, and this is constant eventually. So we can write down from here del S del V equals to alpha by beta. So del V we have to find out. It will be del S beta by alpha, and this will be for 1 mole. Okay. Hmm. Change in molar volume, obviously. So now You have to just put the values. So del V is del S is the del S. Entropy change 2 joule Kelvin inverse, 2 joule Kelvin inverse, mole inverse. So that means it's for 1 mole. So it will del V eventually the del V bar. Okay. Alpha and beta. What is alpha? Alpha is 10 to the power minus 3 Kelvin inverse. So alpha is in the denominator. Beta is there. It is 10 to the power minus 3 1. And you know beta is 9 into 10 to the power minus 4 megapascal inverse. So we have to now do this. What is Pascal? Pascal is Newton per meter square. So Pascal inverse is eventually Newton inverse meter square. So you can write it Newton inverse meter square, and it make mega means 10 to the power 6. So 10 to the power 6 will be there. So it will be 10 to the power 2. And joule is Newton meter, which is Newton meter Kelvin inverse. So eventually Kelvin inverse will be cancelled, Newton will be cancelled. Okay, so it will be 18 into 10 to the power 5 meter cube mole inverse. That's it. That is the del V required. Mole inverse, this is for molar volume. Meter cube is the unit of the volume. So this is the answer. Okay, so this was our. Okay, so now we'll discuss the question number 9. Again, I will first write down the question and then we'll discuss the solution. So let me find out the question first. Okay. At what pressure will ice melt at minus 1 degree centigrade? Assuming that del HF, what is del HF? That means the enthalpy of formation, right? Del HF is independent of pressure and del HF equals to 6.0095 kilojoule per mole. That is given, right? So now we have to we have to identify the pressure value. For this, the ice will melt at minus 1 degree centigrade. And what is given extra? Our information are given information are density of water is 0.9998 gram per cc. So if this value is not mentioned, let's say if this is not mentioned in the question, then we will assume that our density of water is 1. Okay. But here it is mentioned the explicit value. And the density of ice is also mentioned. Density of ice is given as 0.9170 gram per cc. These values are given. Now we have to identify the pressure for which the ice will melt. In general, we know for our normal atmosphere, normal temperature and pressure, which essentially means that 1 atm pressure and in 1 atm, not entity, at 1 atm we know for ice melt in at 0 degree centigrade, right? But we here we want to melt the ice at minus 1 degree centigrade. So that means we need to increase or decrease. We have to change the pressure. For 1 atm, it will not work. So it's clear that we need to apply Clausius equation. So eventually we use the Clausius equation. That is, we can directly use the Clausius-Clapeyron or we can use the Clausius equation. What is the Clausius equation? We know Clausius equation essentially is that del P del T equals to del H by P del V. Now this change is for solid to liquid, water and ice. Okay. So as it is solid to liquid, we have to this del H eventually del H F equal to del H for solid to liquid, that we know. Del V, del V we can also calculate. Okay, okay, okay. Now we can proceed. How? So dP will be del H by T del V into dt. Now we have to make integration. So it will be delta P equals to del H by del V, and this integration will be dt by T. So what is dt by T if you integrate it? So okay, ln T. So essentially it will be ln T. Now if you put limit, del P is, let's say it is P1 to P2 and it is P1 to P2. So it will be eventually del P is eventually P2 minus P1, and there will be limit for T1 to T2. So it will be ln T2 minus ln T1. So eventually you can write ln T2 by T1. So this will be our expression. Okay. If I'm not wrong, yes, I think so. Why we can take del H outside? Because it is considered that it is independent of pressure. Okay, it is independent of pressure or temperature, whatever. But we can't use this for one because del you can use the Clausius-Clapeyron equation for the transition from uh, solid to gas or liquid to gas. But for solid to liquid, we can't use, because for solid to liquid the volume del V is not volume of solid and volume of liquid very close to each other, so we can't approximate that. Okay, so we have to use this formula. Yes, so this is correct. Now we have to just put, we need, let me put here T2 minus T1. Now again read it, the question. Yes, so we know if P1 is, let's say P1 is 1 atm, then we know T1 is what? 0 degree means 273 Kelvin. And now we want that ice, so that ice melt at minus 1 degree centigrade. That essentially means that T2 is 272 Kelvin, right? So P2 will be T1 plus del H by del V, and this del H is essentially del HF. So it is ln 272 by 273. Okay, okay. And now we have to calculate this quantity del HF by del V. This is important. So first of all, del HF is given, we know, but del V, what is del V? Del V is we are considering melting. Melting means solid to liquid. So VL minus VS, we have to calculate this. Now we know density, we know again, we know density D is eventually M by V, correct? Or we can write V is equal to M by D. So it can be written as mass of liquid divided by density of liquid minus mass of solid divided by density of solid. So, and we know mass never changes. Mass will not be changed. Mass will be constant, correct? So there will be change in essentially the density. Now what is the mass? Okay, let to mass take common this is, so it is 1 by dl minus 1 by ds. And what will be the mass? Mass will be, m will be, for 1 mole we can easily calculate. For 1 mole it is 18 kg, correct? You know, we know, let me write, we know molar mass of water 18, right? That is 18 gram per mole. Okay, so 1 mole of water having the have the mass of 18 gram. So here we can write 18 kilogram. So that's why. So to this, wait a minute, let me connect it again. Okay. So 80 into 10 to the power minus 3 kilogram per mole. And this value 1 by dl. What is dl? Density of liquid water, that is given as 0.998, no, sorry, 9998 gram per cc. Cc means centimeter cube. And the solid is 0.9170 gram centimeter cube. So it's not needed eventually. Let remains it is as gram. So it is 1 by 0.9978 minus 1 by 0.9170. And what will be the unit? Just reverse. That means unit will be gram inverse centimeter cube. So this will be 18 into, what will be the value of this? Let me calculate. It is 1 divided by 0.9978 minus 1 divided by 0.9170. Okay, so it is minus 0.08830 centimeter cube mole inverse. Okay, so this is our value del V. This is our del V. So del HF by del V will be, what is del HF? Del HF is given as 6.0095 kilojoule. So into 10 to the power 3 joule per mole. And it is 1.5895 centimeter cube mole inverse. So it is eventually be 6.0095 divided by 1.5895. So it is 3.7807 into 10 to the power 3 joule per centimeter cube. Okay, and joule is Newton meter. So we can write Newton meter into centimeter cube, and 1 meter is 10 to the power 2 centimeters. So it will be 10 to the power 5, and it will be okay. So this is our del H by del F. Or directly we can convert it in meter. It will be just 1, and it will be meter to the power minus 2. So so it is minus 37.007 Newton meters. So it is Pascal. Correct? Okay. So now E2 is U1 plus 37.807. This is Pascal, means Newton per meter square, into ln 272 by 273. What will be the value of this? Ln, okay. So it is again a negative 0.002669. So into minus 37.807. So eventually it is Q1 plus 0.13874 Newton per meter square. Okay. So now this is in Newton per meter square, not in atmosphere. But we know P1 is 1 atm. Now we have to convert atm into atmosphere. Okay. So how you can convert that? So best way is R value. If you remember the R value, then you can easily do this, because we know PV equals to nRT. So R is essentially this trick, PV by NP. So what will be the unit of R? P, unit of P. So it is, let's say, atmosphere, volume, liter, N, mole, and Kelvin. So liter, atm, mole inverse, Kelvin inverse. And we know R, the value of R is 0.08 joule in liter atm. Okay. Again, R has you. We can write down unit of R. PV. What is P? Newton per meter square. What is V? Meter cube. What is this is same. So it is Newton meter means joule per mole per Kelvin inverse. Correct. So again, R equals to 8.314 joule mole inverse Kelvin inverse. Now we can equate this. So we can write 0.082 liter ATM equals to 8.314 joule, and joule is Newton meter. Correct. So we can write it 0.082 ATM into 1 liter, and 1 liter is decimeter cube. This is 8.314 Newton meter. So we can write Newton into, okay, Newton meter, no way, Newton meter, no problem. So now 1 decimeter cube. So 1 decimeter equals to 10 meter. So 1 decimeter cube will be 10 to the power 3 meter cube. So 0.082 ATM is eventually 8.314 into 10 to the power minus 3 Newton per meter square, which is Pascal. So 1 ATM is eventually 8.314 into 10 to the power minus 3 divided by 0.082 Newton per meter square. So this value we know. So P2 will be, what is the value then? We can write 8.314 into 10 to the power minus 3. 10 to the power minus 3 divided by 0.082. So it is eventually 0.1013 Pascal. Okay, so P1 is, sorry, this is P1. So P2 is P1, P1 plus 0.13874 Pascal. So putting this value 0.1013 plus 0.13874 Pascal, it will be eventually 0.13874. So it is 0.2410 Pascal. Now again we have to convert it into ATM. So from here we can write 1 Pascal equals to 0.082 into 8.314 into 10 to the power minus 3 ATM. So 0.24013 into 0.082 divided by 8.314 into 10 to the power minus 3 ATM. So again it is 0.082 divided by 8.314 2000. So it is eventually 2.368 ATM. Okay, so this is the procedure. Please check if there is any numerical error with calculation that may be there, but the procedure is like this. We have to use the Clausius equation, not Clausius-Clapeyron. Then we have to convert this ATM to Pascal. Okay, so this was our question number 9. Okay, so now going to question number 10. Wait, the question number 10. Let me just find it out. Okay, this type of question we have done already, but let's do this again. The characteristic rotational temperature theta for H2 gas is 87.5 Kelvin. Then what is the value of the molecular partition function? For rotation. For rotation at 3000 Kelvin. So what is given? Theta r is given 87.5 Kelvin. And we have to calculate. We know that QR equals to P by sigma into theta. Sigma is our symmetry number. And H2. For H2, we know sigma is 2. Correct. So we can write it. We have to find out the partition function. So it is T, that is 3000 Kelvin, and it is 2 into 87.5. This is very, very trivial question. And it is 17.14. Okay. Now it is question number 10. So now going to question number 11. Okay. Okay. The question is big question. A 50 gram mass of copper at a temperature of 393 Kelvin is placed in a contact with a 100 gram mass of copper. Okay. At a temperature of 303 Kelvin in a thermally insulated container. Calculate Q means the heat and del S total for the reversible process. Use a value of 0.4814 joule gram inverse Kelvin inverse for the specific heat capacity of copper. Okay, so that is a 50 gram mass of copper at a temperature of 393 Kelvin. That is in contact with a 100 gram mass of copper at a temperature of 303 Kelvin. In a thermally insulated container. Means, let's say this is a thermally insulated container. There is two pieces of copper. This is one piece, and let's say this is another piece. This is 50 gram, and this is 100 gram. Great. So we have to calculate the Q. Obviously, heat will be heat will be coming from the hot copper to the cold copper. It will be passed from the hot copper to cold copper. It is clear. And we have to calculate the del S total for the reversible process. Consider this is a reversible process that we have to consider. So we know for heat exchange, we know from our BS class 2 level that M into heat capacity C del T for mass, any mass, it's M C bar del T prime. So we know this formula. Let's say, or in general, we can write there are two body A and B in different temperature. Then we know MA CA del TA equals to MB CB del TB. That is we know. Where C is the specific heat capacity. So here we can write. So for here we can write uh, M A, which is 50 gram heat capacity of copper, that is also known to us, but that heat capacity is both are copper here. So that will be cancelled because these both will be C. So that will be cancelled. Both are copper here. Now it is del TA. Del TA is, let's say, we have to find out, it's 393 to, it will be equilibrium eventually. So we have to find out that T. So for 50 gram of copper, it is higher temperature. So temperature will be decrease. So it is 393 minus T. MB is 100 gram and it is T minus 303. So we have 393 minus T equals to 2T minus 606. So 3T is eventually, so 3T is 606 plus 393. It is 999 divided by 3. Okay. So temperature will be 333 Kelvin. Correct? This is all first question. Now we now we have to calculate the del S total and amount of heat. Okay, Q. Consider any M C del T. Let's say 50. What is C? C is 0 point. Everything is, this is in gram. It is 0.4184. Do it clearly. So Q will be M C del T. So M is 50 gram. C is 0 point, that is given in the question, 4184 joule gram inverse Kelvin inverse into del T. What is del T? 333 and it was eventually 393. So it is 60 Kelvin. So only joule will be there. So it is 50 into 60 into 0.4184. So it is 1255.2 joule. So this amount of it will be exchanged. Now we have to calculate also the del S. For the A, species A, let's say it is, we know this will be NCPLN. We have to remember this formula, right? NCPLN T2 by T1 plus minus NRLN. Here is NCP. So probably there will be P2 minus T1. NRL, if it is CV, then it will be V2 minus V1 and the sign will be changed. But here we have to keep in mind that the temperature is only changing. Pressure, volume are same. So this value will be 0. So NCPLN T2 by T1. Okay. Now what is N? For copper, molecular weight of copper is 63 gram. Correct. So it is 50. Okay. What is CP? That is given. CP is given. Okay. Because these are all are happening at a constant pressure. So CP is given as already we have used, that is 0.4184 joule gram inverse Kelvin inverse. And this is ln this. So just we have to do this. So ln 333 divided by 393. Okay. Into 0.4184 into 50 divided by 63. So it is minus 0. Okay, there will be another, sorry, there will be here 63 gram per mole inverse also be there. Why? Because this is molar heat capacity. This is molar heat capacity for 1 mole. Okay, okay. Then there will be also, okay. This heat capacity joule per, no, this is joule per gram inverse. Correct, correct. Joule, entropy should be joule per gram. CP is capacity for 1 mole eventually. This value, this if you multiply it, it is coming with joule. Correct. What is the unit of entropy eventually? Entropy is Q equals to ds equals to d cross Q by T. Okay, this is joule per Kelvin. Joule per Kelvin. So it's correct, no problem. So, but here 663 should be multiplied. Then it will be joule per Kelvin. So when you are multiplied with NCP, then uh, for this formula, the CP is eventually the CP bar for 1 mole. Okay. And 63 gram per mole will be there. That is the molar volume. Okay, so this is our formula. Let's probably it's clear because we know this value, CP value is given, right? Let us discuss. What is CP? Cp is d cross q dt by v. So what will be the unit of Cp? Q is heat means joule and temperature Kelvin. So joule per Kelvin. So it is the unit. But let look. This is there is a gram inverse means for per gram. This is for per gram. That's why you have to multiply it with the 63. When you have put mole here in mole, so you have to now multiply it with the uh, heat capacity for 1 mole. That's why you have to multiply the 63 gram because for 1 mole there is a 63 gram for copper. That's the case. So just we have to multiply it with 63. So it is okay. So uh, what will be the value now? I think this is clear. Let me clear it. What is Cp? Cp is eventually our we know del Q by del T at constant pressure. And this what will be the unit of Cp then? The unit of Cp will be joule per Kelvin. So you can see, but here the unit has given the unit is given as this joule per gram inverse Kelvin inverse. That means this Cp value is given for 1 gram, for 1 gram only. Now you are considering the number of moles. Okay, so because you have put this is n number of moles. Okay, for that we here we have to consider the Cp bar, that is the molar heat capacity. Then what will be the molar heat capacity? Cp bar will be Cp into 63 because this Cp for 1 gram and we know for 1 mole there is 63 gram of copper. So that's why it is multiplied with 63 and this value is eventually 3.466 joule per Kelvin inverse. So now what will be del SB? Similarly, del SB also will be here it will be 50 gram. Oh, sorry, 100 gram divided by 63 gram per mole into similarly 0.4184 joule gram inverse Kelvin inverse into it should be multiplied with 63 gram per mole ln 303 divided by 3 333 divided by 303. Okay, so if you do this calculation, it will be 60 will be there, so it will be 3.950 joule per Kelvin. Hence, del S total, what will be del S total? Del S total will be del S A plus del S B. So it is minus 3.466 joule per Kelvin plus it will be 3.950 joule per Kelvin. So to add it, so it will be 0.4854 joule per Kelvin. Okay, so this will be our this total. So let me stop here today. So we have already discussed 11 questions in this class. So please gone through this lecture. I will upload the video, YouTube link in the spreadsheet, and please gone through the lecture. If there is any doubt, you can ask me in the next class, or you can also message me. Uh, Now remaining 3 classes, similarly I will discuss various type of questions from various part of the courses. Uh, so you can also ask your doubts that will also be solved in the next classes. So let me stop here. Now I'm stop sharing. Okay. Okay. Please now gone through the lecture video. I will upload it in YouTube and I'll share the link. So please. Okay. So let me stop here today. We'll meet again in the next class. Okay. Thank you.